Next topic we're going to look at is correlation and regression, starting with the first topic, correlation. Now we are looking at correlation. The key concept is, in addition to hypothesis testing and confidence interval, inferential statistics determines if a relationship between two or more quantitative variables exists.
A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. A linear correlation exists between two variables when there is a correlation and the plotted points look like a straight line.
This section considers only linear relationships, which means that when graphed in a scatter plot, the points approximate a straight line pattern, and methods of conducting a formal hypothesis test that can be used to decide whether there is a linear correlation between all population values for the two variables. The linear correlation coefficient R is a number that measures how well paired sample data fit a straight line pattern when graphed, measures the strength of the linear association between the two variables. Use the sample of paired data, sometimes called bivariate data, to find the value of R, and then use R to decide whether there is a linear correlation between the two variables.
Regression is a statistical method used to describe the nature of the relationship between variables, that is, positive or negative, linear or nonlinear. Questions. Are two or more variables related? If so, what is the strength of the relationship? What type of relationship exists? And what kind of predictions can be made from the relationship?
The synopsis of the section is that correlation deals with the relationship. Are they related? By the way, when we establish that, it doesn't mean if there is a causal effect. There is no cause. We are just establishing the relation. It's bivariate. We're dealing with two variables, x and y. And if there is a relationship, what is the strength? And the relationship may be linear or nonlinear. We are interested in a linear relationship as far as this one is concerned, okay? A linear correlation. And if it's so, can we use prediction? Meaning, is there a way to come up with something that can predict what's happening in the future, which means you come up with an equation of a line known as a regression line, which is the best line of fit, and you can predict what comes up. So that's the idea behind regression and how we put all of this together. So as far as a scatter plot is concerned, and you can see it on the right side, basically you plot points. That's all you do. X is the independent variable, Y is the dependent variable. And I hope everybody remembers when we were dealing with algebra, slope-intercept form was y equals mx plus b, where m was the slope and b was the y-intercept. And so if m is positive, you have the first type. Take a look at the top one. If it's negative, you have the second one. And the other two, the third one doesn't have anything as far as correlation, doesn't show anything. And the last one, it is nonlinear, and some of you may realize it's quadratic.
Distinct straight line or linear pattern, we say that there is a positive linear correlation between x and y, since as the x values increase, the corresponding y values also increase.
Distinct straight line or linear pattern, we say that there is a negative linear correlation between x and y, since as the x values increase, the corresponding y values decrease.
No distinct pattern would suggest that there is no correlation between x and y.
Finally,
distinct pattern suggesting a correlation between x and y, but the pattern is not that of a straight line.
Part A, basically, x gets larger, y gets larger. Part B, x gets larger, y gets smaller. Those are the two that we are interested in. If we come up with a scatter plot that looks like part C, there is nothing we can say. Now, when is lost? So if you go back to the numbers at the bottom, it gives you R, which is the correlation coefficient. This is fairly large. So is this one in an absolute value. So R represents the strength of the correlation, and it's between -1 and 1. And that's important to understand. If it's close to 1, it's strong. If it's close to negative one, it's strong. And if you look at part C, there is no correlation. And as I mentioned in part D, there is no linear correlation, but you may see a quadratic relationship. There is a relationship. Are two or more variables related? If so, what is the strength of the relationship? To answer these two questions, statisticians use the correlation coefficient, a numerical measure to determine whether two or more variables are related and to determine the strength of the relationship between or among the variables. Linear correlation, R, the linear correlation coefficient R, measures the strength of the linear correlation between the paired quantitative X values and Y values in a sample. It determines whether there is a linear correlation between two variables.
There are two types of relationships, simple and multiple. In a simple relationship, there are two variables, an independent variable, predictor variable, and a dependent variable, response variable. In a multiple relationship, there are two or more independent variables that are used to predict one dependent variable.
There may be more than one independent variable. Remember, in the case of y equals mx plus b, y depends on x. By the way, sometimes you can interchange it. What happens when you have more variables? That also can be discussed. But in this case, we're interested in one variable for independence. So with that being the case, let's finish up number 4.
Predictions are made daily in all areas. Examples, weather forecasting, stock market analysis, stock market analyses, sales predictions, crop predictions, gasoline price predictions, and sports predictions. Some predictions are more accurate than others due to the strength of the relationship. That is, the stronger the relationship is between variables, the more accurate the prediction is.
So the point is, this is a very important branch of statistics, and it works better in some cases than others. Okay, depends on the strength between the variables or among the variables. In many cases, by the way, you have a lot of variables to consider, but the concept comes from this idea of correlation. Let's look at a very simple example. We are given the table and we want to construct a scatter plot for the data shown for car rental companies in the United States for a recent year. We have different companies, A, B, C, D, E, F, bunch of companies, and the cars in 10,000s, and then the revenue in billions. So company A, for example, we see two numbers in front of it, 63 and 7.0. That means 63 times 10,000 or 630,000 and $7 billion in revenue. Just as an example, company B, 29.0, that means 29 times 10,000, 290,000 cars, and then revenue is 3.9, that means $3.9 billion. Obviously, the rest follows, so that shouldn't be a big deal at all. You want to come up with a scatter plot. In short, it means that you have the x and y axis. Okay, so look at this. This is the pair. This is one pair. So we want to draw and label the x and y axis and plot each point on the graph. So for example, the second pair would be 29, 3.9, and the rest of it. So we have 1, 2, 3, 4, 5, 6 pairs, and we're going to plot the points. I don't think anybody has any problem in points. You just got to be fairly careful, especially when you have a small size data, and plot accordingly. So just for the sake of argument, if we call this the very first pair, this would be the one. You see that, everybody? First pair. Okay, 63, 7. So the x-axis cars in 10,000s, the y-axis the revenue in billions of dollars. Okay, So I hope it is clear to everybody. Just as an example, if this is pair number 2, okay, this is pair number 2, okay, 29, comma 3.9. We can easily see the pair, and we have an idea how we come up with the rest. I want to quickly go over technology if you want to use that, but this is very simple and straightforward. So to do that, first you clear the list, you put the data into L1 and L2. So you start edit clear list L1 and anything else L2, and you put it, you just input the data. Then I'm going to press on Y and clear, and second Y scatter plot, enter on, enter, select X1, list as L1, and so on and so forth. This is very straightforward. This is a detailed one. It shows you what to do. Okay, so take a look at what happens here. Now, the last one, mark, is what you put in. You want it to be dots or plus, whatever that you decide. It's just a mark showing what comes up. If you do the drawing, whatever you choose, it shows up here. So this is your scatter plot. Obviously, for a simple case such as this one, you can just do it by hand. It's really not that big of a deal. I believe everybody can do that. So again, first input L1 and L2, and then go to the scatter plot and enter that. This is how we construct a scatter plot. The correlation coefficient computed from the sample data measures the strength and direction of a linear relationship in two variables. There are several types of correlation coefficients. The one explained in this section is called the Pearson product moment correlation coefficient, or PPMC. And so Pearson product moment correlation, or simply a correlation. And we use rho to represent that for the population. Now, as you can see, the strength here, it shows the strength. If it's close to 1, is strong. How close is close? You really have to do the test of hypothesis to make a decision. But normally 0.7 and higher is good, negative 0.7 and less is good.
The correlation coefficient computed from the sample data measures the strength and direction of a linear relationship between two variables. There are several types of correlation coefficients. The one explained in this section is called the Pearson product moment correlation coefficient. The symbol for the sample correlation coefficient is R. The symbol for the population correlation coefficient is P. The range of the correlation coefficient is from -1 to +1. Sorry.
That's fine.
If there's a strong positive relationship between the variables, the value of R will be close to +1, 0.7 or larger. If there's a strong negative linear relationship between the variables, the value of R will be close to -1, -0.7 or smaller.
We use R for sample correlation, and for population, we use rho. These are just symbols. N is the number of pairs, summation of x is summation of all x's, summation of x squared is sum of x values that are squared, summation of x quantities to the square, that means add them up, and then, and we want to definitely avoid confusing these two, because I've seen that sometimes students don't distinguish between the two, okay? We've been through that when we did the standard deviation, so we should be fine. Summation of x y indicates that each x value should first be multiplied by its corresponding y value, and then add them up, basically. R is the linear correlation coefficient for sample data. Rho is a linear correlation coefficient for a population of paired data. So, given any collection of sample paired quantitative data, that's the key, quantitative. has to be quantitative. So we can come up with the linear correlation coefficient R. So the linear correlation coefficient R can always be computed, but the following requirements should be satisfied when using the sample per data to make a conclusion about linear correlation in the corresponding population of the paired data. So with that being the case,
the sample of paired XY data is a simple random sample of quantitative data. Visual examination of the scatter plot must confirm that the points approximate a straight line pattern. Because results can be strongly affected by the presence of outliers, any outliers must be removed if they are known to be errors. The effects of any other outliers should be considered by calculating R with and without the outliers included. In other words, requirements 2 and 3 are simplified attempts at checking that the pairs of XY data have a bivariate normal distribution.
outliers can create a problem. That's why we want to be careful of those for a simple reason. When we do the correlation and we do the test of hypothesis on that, ultimately the idea is that to come up with a regression line that works. And the regression line is extremely affected by outliers. That's why we want to check for that. And I'll explain that as we come across examples of that. All right, as you can see, R is very complicated. Needless to say, you have access to it as far as the formula is concerned. You can use the formula sheet to use that, and we can use technology to evaluate it. So you are exposed to both of them. But R is n summation of x1 minus summation of x times summation of 1 over the square root of n summation of x squared minus summation of x quantity squared times n summation of y squared minus summation of y quantity squared. Very complicated, but no worries. You have that. Now, there is another way of saying the same thing. Z sub x denotes the z-score for an individual sample value x. Z sub y denotes the z-score for the corresponding sample value y. R is summation of z sub x, z sub y over n minus 1. The difference is this is easier to grasp and understand. How do you come up with z sub x? You look at just the x values and you calculate the z-score for each one, which is z equals x minus mu over c. We'll go over that just for the sake of argument to see how it's done. So there are two ways to calculate it. The second method is easier to understand the concept. All right. So let's look at an example to see how this thing goes. So here's a table. The table lists 5 paired data values using technology to find the value of the correlation coefficient R for the data. The idea is that normally we use technology. So if we look at what's given in technology, take a look at what is boxed in red. That is the value of R. So if you're using technology, so from the technology, StatDisk, Minitab, StatCrunch, Excel, StatTI, the value of R will be automatically calculated, and all of them give you something like 0.795 and show you how it's done by hand. So given that, and that's the formula. So I want to show you that it's really not that bad when you have just a few pieces of data and you want to calculate. Look at the formula. According to the formula, we need to calculate summation of x, summation of y, summation of x squared, summation of y squared, summation of xy. So let's come up with this table. First, x and y we write it. Then we add x squared column. 5 squared becomes 25. 6 squared becomes this. Is this table squared? So this one squared, and you get to that. Square these numbers, and you get these numbers. Multiply these two numbers, and you get this. Multiply these two numbers, and you get this. The process may be long and tedious, but the concept is extremely simple to understand. So what do we do now? We add one more row at the bottom. We add all those in the column. So the x column, we add them up. The y column, we add them up, so on and so forth. So when we add them, those are the numbers. Now look at the top formula in blue. You have everything. A being number 5. Just plug in 5 times summation of x bar is 159 minus summation of x is 24 times summation of y is 31 over the square root of, and summation of x squared is 118 minus summation of x is 24 squared. You close the brackets, and the new brackets, n is 5 times summation of y squared, which is 251, minus summation of y, which is 31 squared. Do the math, you come up with the answer, 0.795. Now, what if we wanted to do it with TI? You put the information in L1 and L2, and TI calculator linear regression test will give you the value of R. You have to do that. It gives you more than that, but you have to do that. So you use that stat test, linear regression t-test, enter L1 and L2. If we want to choose whatever, in this case, not equal. Take a look at what happens when you put that. So X1 list is L1, Y1 list. It is normally that. As long as you put L1 and L2, as long as you do this part, when you want to go to the linear regression t-test, it is L1 and L2. Basically, you have to just enter, and all the way to calculate. Really, you don't have to put in much because normally, unless you don't put the information, the data into L1 and L2. And here's the result. So what I want you to pay attention to, because of the arrow here, I'm showing you the second part. Okay. Now, it gives you the test of hypothesis for the correlation coefficient with the p-value. It gives you A and B, y equals A plus bx. This is the regression line with A being negative 11 and B negative 11.2857 and so forth. And B is 3.6428 so forth. So what is it that we need? We are interested in this one, and we have no choice but to go through the process to find it. So if you want to go with the technology, you have to go this far. So for this question, I want to show you the second formula that was discussed, again by hand. But mostly things will be done with technology. What I want to do, I want to use this formula, z sub x, z sub y over n minus 1. Okay. Now, this formula has the advantage of making it easier to understand how R works. The variable x is used for the chocolate values, and the variable y is used for the noble values. Each sample value is replaced by its corresponding z-score, z sub x and z sub y. I will show you how to calculate just one of them, and then you'll see how the rest goes. And again, that will take some time. Okay. So z sub x is calculated, z sub y is calculated. You multiply. So these two columns are being multiplied. So the first one would be 0.239046 times negative 0.052164, giving you negative 0.012470 as an example. This times that equals this. Okay. And now this very last column, add them up. Okay, that's the summation. Add them up. That is your numerator class. So the z-score for all the chocolate values, see the third column. The z-score for the noble values, the fourth column. And the last column is the product. Okay, everybody? Put it into the formula. N is 5, so 5 minus 1. And you get to the same answer. Now, how do we calculate z sub x? I want to show you, I want to remind you. Okay? You need to look at the x's, and for this data, you have to find x bar. That means you add them up and divide by 6. And you have to find s. Okay, it's the summation of x minus x bar quantity squared over n minus 1, and it has to be the square root of that. And then z is x minus x bar over s. This is the square root, everybody. Okay. So that's, everybody remembers how we calculate the z-score. The z is what? X minus mu over sigma, or x minus x bar over s. So that's how you calculate it. So for example, for the very first entry, okay, number 5, okay, x is 5, x bar is calculated as 4.8, 5 minus 4.8, and divided by s, which is 0.83666, and it gives you 0.23905. So I hope you see that this number is this number, everybody. So if you can calculate 1, you can calculate all. Does it take long? Yes, it does take some time. Look at the next example. Finding the correlation coefficient. Understand that we don't do that by hand. We do it with technology, but again, just to be exposed to the process, let's do that. If you look at the formula, you can see x times y and the summation of that. You need summation of x, you need summation of y, you need summation of x squared, summation of y squared. And so, of course, the first column is the name of the companies, the second column, we add them up, the third column, we add them up, we multiply, and so on and so forth. So take a look at what happens. This is x times y. For example, the first one is 63 times 7. X squared, for example, the first one is 63 squared. Y squared, for example, the first one is 7 squared, or 49. Now, simply add them up. Now, all you have to do, write those. There are 6 pieces of data or pairs. Put your findings into the R formula. Carefully do your calculation. You get 0.982. As you can see, it's a fairly large number. It's extremely close to number 1. So even if we don't do the test of hypothesis and we do it and we see what it means in a moment, we should recognize this is really a strong relationship, or specifically strong positive relationship. Now, as I mentioned, this is really not done by hand. So if you do it with technology, look at the bottom number. So we are interested in R. R squared is also there. So I will go over the concept shortly. This is really known as what explains the variation of those variables, one with respect to the other. We'll discuss that as we come across it. I just wanted to show you that the technology does the job for us and gives us R. Not only that, it also gives us regression formula y equals a plus bx. In this case, b is given. If you scroll down, you see the value of a also. But for now, I just want to move on. We were interested in the value of R only for now. What happens next, we'll see in a moment. We need to know what is the test of hypothesis in regards to correlation coefficient. And that's why the R is calculated. The null and alternative hypotheses are always the same. H0, rho equals 0, which means no correlation. H1, rho is not equal to 0, which means there is a correlation. So I want to make sure we understand what we're trying to say here. This is not going to change. When we do the test of hypothesis, this is the same for this type of test, always. So if you happen to reject H0, that means there is a correlation. So null hypothesis stays the same, alternative hypothesis stays the same. Now, and you all remember the concept as far as the p-value goes, because most of the time this is done by technology, and the technology gives you the p-value, in which case, when p-value is less than alpha or equal to alpha, you reject H0, which means what? H1 wins in essence, which means there is a correlation. And if p-value is larger than alpha, do not reject H0 or fail to reject H0, then there is no correlation.
Using Pearson correlation coefficient table to interpret R. Consider critical values from this table for technology as being both positive and negative. Correlation. If the absolute value of R is greater than or equal to the critical value, there is sufficient evidence to support the claim of a linear correlation. No correlation. If the absolute value of R is less than the critical value, there is not sufficient evidence to support the claim of a linear correlation.
And again, an example makes this clear. So we can use the table for Pearson correlation coefficient. And again, the idea is, remember, this is a two-tailed test. And so you're comparing it with the two-tailed test. That's the idea.
Properties of the linear correlation coefficient are: -1 is less than or equal to R, less than or equal to 1. If all values of either variable are converted to a different scale, the value of R does not change. The value of R is not affected by the choice of X or Y. Interchange all X values and Y values, and the value of R will not change. R measures the strength of a linear relationship. It is not designed to measure the strength of a relationship that is not linear. R is very sensitive to outliers in the sense that a single outlier could dramatically affect its value.
Very important to understand, R is always between -1 and 1. Close to 1 is a strong relationship, and strong R, and close to -1 the same. And if you recall, we said roughly 0.7 and larger, or -0.7 and smaller. If you interchange X and Y, the value of R doesn't change. R says, is there a strong relationship or weak relationship between the two? And of course, outliers can have a dramatic effect. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. We are going over the synopsis of this again. A linear correlation exists between two variables when there is a correlation and the plotted points look like a straight line. The linear correlation coefficient R is a number that measures how well paired sample data fit a straight line pattern when graphed. In other words, it measures the strength of the linear association between paired data, called bivariate data. The value of R squared is the proportion of the variation in Y that is explained by the linear relationship between the two variables X and Y. Now, obviously, this is the formula. You've seen it before. The properties between negative and positive 1, that's the values of R. And as you recall, these are the steps involved when we do the test of hypothesis. Okay, we write H0 and H1, we come up with test statistic, critical value, we make a decision. Okay, and the thing you want to remember is the idea of the T, okay, and how you arrive at it is that T is R squared of n minus 2 over 1 minus R squared. And by the way, the two are the same. If you look at the formula, the next one says R over 1 minus R squared over n minus 2. I hope you see that the two are the same. Okay, if you just show you that. If you look at these two formulas, my point being this and this one are the same. Understand what's happening here. If you look at this one, the second one, if you will, it's R times 1 over the square root of 1 minus R squared over n minus 2. This is the reciprocal, if you will. Okay, 1 over anything is the reciprocal of that, and this part itself is the same as square root of n minus 2 over 1 minus R squared. The reason I'm putting up both formulas, again, some texts, they like to show the first one. Some texts, they use the second one, but they're identical. And the degrees of freedom is df equals n minus 1 minus 1, because there are two pieces of data. So n minus 2. Okay, and also you see if you look at the formula in green, we would write r minus mu sub r. Again, mu sub r comes from h0 and it's always a 0, mu sub r referring to the r itself in essence. Okay, let's like this, put this in slide mode again. All right, let's do the test of hypothesis here. And there are two ways to do that, and I want you to be exposed to both methods. Needless to say, you don't have to do both methods, but let's see how it works and what do we mean by that. Let's go with the steps. The very first step, as you know, is H0 and H1. H0 row equals 0, H1 row is not equal to 0. And if you're interested in checking for relationship, we are claiming that, you know, H1 is true and that is always a two-tailed test. So this would be your H0 and H1 always. Now we have two methods. One of them is using t-distribution. One of them is using the Pearson correlation coefficient. In fact, that is the table that you're looking at. So those are the two methods. We're going to go through each and every one of them. Okay, so if we are going with the t-distribution, look at the top formula. The formula for t is given, okay, and we need the value of r to calculate it. We just plug in. So take a look at the formula. T equals r 0.982 times the square root of n minus 2, 6 minus 2, over 1 minus r squared, 1 minus 0.982 squared. Okay, you do the math, you come up with the test statistic for the t-distribution. Critical value is what? Well, critical value comes from the choice of alpha. Alpha is 0.05. Degrees of freedom is n minus 2, that means 4. And we can find the value of t, which is plus minus 2.776 from the t table or technology. Okay, fine. How do we find the test statistic using the second method? Test statistic is given to us, class. Test statistic is the value of r that either has been given to us or we have calculated it, 0.982. So that one is given. Okay. What about the critical value? The critical value comes from the Pearson correlation coefficient table, the table to the right. Okay, so what are we looking for? Alpha is 0.05. So look at alpha of 0.05 column. Then what about n? Okay, n is 6. So in front of that, we are looking for the number. So look at number 6 is your n. Look at your alpha. And therefore, the answer is 0.811. So that wasn't too bad. Okay. Now, to make a decision, let's look at graphs. Okay. So if we look at the graph for the first one, notice what happens. You have t equals plus minus 2.776. We have that. And look at the test statistic. The test statistic is way into the rejection region, 10.398. So it's way into the rejection region. You're going to reject that if you use the t-distribution class. I hope it's clear. Look at the second method. The numbers we got as critical values are 0.811 and negative 0.811. Test statistic is 0.98. It's way into the 0.982 class. It's way into the rejection region. Rejection region, everybody. So I hope that's clear. And therefore, the decision is clear also. You're way into the rejection region, so reject H0. When you reject H0, the claim becomes true, and that means there is a significant relationship between the two variables. Okay, so I hope everybody is clear as to how we arrive at the answer here. Okay, it's very straightforward, and you don't have to do both methods. We do that for practice. Okay, and we are going to look at one more example to get comfortable with this concept. And we revisit that in the next section. Could somebody read this question for us, please?
Given the value of R equals 0.801 for 23 pairs of data regarding chocolate consumption and numbers of Nobel laureates, and using a significance level of 0.05, is there sufficient evidence to support a claim that there is a linear correlation between chocolate consumption and numbers of Nobel laureates?
Thank you so much, Laura. Okay, class, remember, we have to calculate the R. It's given to us, so it makes life easier. So I hope you see that pretty much everything that we want is given. The value of R we need is given. N is given. Alpha is given. Okay. So this is R again. So let me erase that. For some reason, the pen is bleeding, doesn't do the job. And so H0 and H1, we are repeating the same thing. H0 row is 0, H1 row is not, and that is a two-tailed test, and that is the claim. So let's do the test statistic. Look at the formula. We are going with the method 1. So T distribution is used here. So R is given, N is given, plug in. So T becomes 0.801 times the square root of 23 minus 2 over 1 minus 0.801 squared, resulting in 6.1314. This is a two-tailed test. Okay. Alpha of 0.05, degrees of freedom of n minus 2 or 23 minus 2. And we use the table. We end up with plus minus 2.080. And that's as far as the T distribution goes. If we go with the Pearson table, Pearson coefficient, test statistic is given to us 0.801. Okay. As far as the critical value is concerned, the critical value alpha is 0.05, so we look up that table. N is 23. So the table, I want you to pay attention. I've given you just those two rows. The table contains number 20 and number 25. There is no 23. So what is the critical value? I hope you see that the critical value is not there. So what is it? It's between the two numbers. The second column represents alpha of 0.05. I hope you remember that from the previous page. So from the previous page, I'm just showing you those two. So it's between the two numbers. Okay. if you use the technology, it gives you the answer 0.413, even plus minus. Even without the technology, it is pretty straightforward that you are comparing this with the test statistic of 0.801, which is way into the rejection region. So let's look at the graphs. This is the graph for the t distribution. Obviously, test statistic is beyond 2.080. It puts it in rejection region. If you look at the other one, okay, what happens? Basically the same thing. Now, even if you don't pay attention to technology and you just look at the numbers you came up with, okay, the best case scenario or the worst case scenario, 0.396 or 0.444, somewhere in between. 0.801 is beyond both of them, okay? And therefore, it puts you in the rejection region, and the rest is very clear. You make a decision, you're going to reject H0. Therefore, the claim becomes true, and there is sufficient evidence to support the conclusion that there is a correlation. So, for countries, there is a linear correlation between chocolate consumption and numbers of Nobel laureates. That is referring to the type of data we were dealing with. And so, we shouldn't, of course, forget the following. Okay, although we have found a linear correlation, it would be absurd to think that eating more chocolate would have been a Nobel Prize, because that was the idea of, among the two pieces of data. And the thing is, you can always find a correlation, but it may not mean anything, one may not cause the other. It's important to understand that. Okay, and so it is the test of hypothesis that is important to understand what it tells us. Now, as I mentioned, the value of r squared was discussed briefly in one of the pages. So the value of r squared is the proportion of the variation in y that is explained by the linear relationship between x and y. Using the 23 pairs of chocolate Nobel data, we got r equals 0.801. What proportion of the variation in number of Nobel laureates can be explained by the variation in the consumption of chocolate? It's simply put, the answer is r squared. Okay, so with r being 0.801, we get r squared equals 0.642. Just square it, class. Okay, what does it mean? Could somebody read the interpretation for us, please?
We conclude that 0.642, or about 64% of the variation in numbers of Nobel laureates, can be explained by the linear relationship between chocolate consumption and numbers of Nobel laureates. This implies that about 36% of the variation in numbers of Nobel laureates cannot be explained by rates of chocolate consumption.
Thank you so much. So this is the interpretation. R squared, explains the variation, and whatever is left simply is not explained by that. So having said that, let's look at the synopsis of what we covered. All right, correlation, possible relationship between variables. When the norm hypothesis has been rejected for a specific value, any of the following 5 possibilities can exist. So when we say there's a relationship, okay, there's a correlation, if you will. Any of this will go. I'd like you to help us understand. Somebody read number 1, please.
There is a direct cause and effect relationship between the variables. That is, X causes Y. Water causes plants to grow. Poison causes death. Heat causes ice to melt.
Thank you so much, Martha. Could somebody read number 2 for us?
There is a reverse cause and effect relationship between the variables. That is, Y causes X. Suppose a researcher believes excessive coffee consumption causes nervousness, but the researcher fails to consider that the reverse situation may occur. That is, it may be that an extremely nervous person craves coffee to calm his or her nerves.
Thanks, Tina. Number 3.
The relationship between the variables may be caused by a third variable. If a statistician correlated the number of deaths due to drowning and the number of cans of soft drink consumed daily during the summer, he or she would probably find a significant relationship. However, the soft drink is not necessarily responsible for the deaths, since both variables may be related to heat and humidity.
Thanks, Mark. Number 4.
There may be a complexity of interrelationships among many variables. A researcher may find a significant relationship between students' high school grades and college grades, but there probably are many other variables involved, such as IQ, hours of study, influence of parents, motivation, age, and instructors.
Thanks, Tina. Number 5.
The re-
The relationship may be coincidental. A researcher may be able to find a significant relationship between the increase in the number of people who are exercising and the increase in the number of people who are committing crimes. But common sense dictates that any relationship between these two values must be due to coincidence.
Thanks, Anna. So I hope you are following what's happening here, and I'd like you to, whenever you get a chance, to really go back and reread this page. So a lot of things can happen, and by the way, as X influences Y, it's the same that YX influences X or not, okay, what it means. And when we find a correlation, does it mean that one causes the other? So there are a lot of things involved here. So it's not a simple yes and no when the correlation is calculated and the correlation coefficient is high and the test of hypothesis is done. It means more than what we just, found. It does require more work to figure out what's going on. Okay. Correlation doesn't imply causality. We know that previously that we should use common sense when interpreting results. Clearly, it would be absurd to think that eating more chocolate would help win a Nobel Prize. Okay, so common errors. Could somebody read that for us?
Common errors involving correlation. 1. Assuming that correlation implies causality. 2. Using data based on averages. 3. Ignoring the possibility of a nonlinear relationship.
Thanks. Finally, hypothesis. Could somebody read that for us?
If conducting a formal hypothesis test to determine whether there is a significant linear correlation between two variables, use the following null and alternative hypothesis to use p to represent the linear correlation coefficient of the population.
Thank you so much, Maria. So remember, in short, when we reject H0, that means there is a correlation.